missed you. I don't know if you missed the videos, but the videos missed you. Very sweet, how sweet. Today we're going to talk about position and velocity. The nice thing is that we can use derivatives, the thing that you've been learning, to solve problems about position and velocity and their relationship to each other. We can solve the problems much better and easier using derivatives. That's right, people. Better and easier. Who doesn't love that? That's what we all want. Okay. So think back to physics your freshman year. And if you didn't go to freshman year here, that's okay. If you haven't taken physics, it'll still be alright. You can still get the gist. So we had a lot of problems with like something going off a cliff. Do I want to draw it like this? I don't think I want to draw it like that. No. Let's get rid of that. Bye-bye. Instead, let me start with my cliff and let's say, okay, if I've got a ball or a person, it's jumping up and over the cliff. Well, I can put my axes kind of wherever I want to, but we're going to start thinking about, by convention, just always placing our axes in a particular place. And we're just going to place them there so that we have some sort of initial position that happens at t equals 0, right? So at 0 seconds, that's our initial position. At t equals 0. And so this is a t versus position curve, and we'll let position be s. So call position s. And it'll be s of t, this is a function of t. Now you learned in physics, you learned about position. And you learned about the parabolic nature of motion. You also learned that the y and the x components actually don't depend on each other. They are independent. The y component does not care what the x component is doing. It's like, honey badger don't care, y component don't care, x component don't care. Alright, you also learned that s of t, so the position due to like the time, support of the time, the position, depending on time, alright, is 1/2 gt squared. It's going to be more complicated than that, but that's what you learned. You also learned that g, sorry, that looks like a y, it's supposed to be g, is negative 9.8 meters per second squared. So that's g. Some more stuff you learned, we'll get to later. So I'm here to tell you that there is more to the story. So g, again it's a g out of y, is negative 9.8 meters per second squared. Or, look, if we don't want to do it in meters, can't g be negative 32 feet per second squared? Yes, it can. So we're going to use both. We'll work with both. And your book works with both. So you got to pay attention to whether or not we're working in feet or in meters. If there's some sort of initial upward, really, or downward, it can be either, but initial vertical component to your velocity, so again, I'm saying, okay, so if there's an initial upward or downward velocity, and we're talking about the vertical component. The vertical component of position can be modeled with s of t is 1/2 gt squared plus v naught t plus s naught. So v naught is the initial velocity, and we set it with like a v naught, like a 0 like that, we call it v naught. And we put 0 because it's at like t equals 0 seconds. It makes sense. The notation makes sense. So S naught is the initial position. Again, we call it S naught. That's how we say it. And naught meaning initial with t equals 0. So, back to the curve. We can look at the curve, and we know it's a parabola of that t squared. So here's my parabola of some kind. There's my S naught. So when I plug in 0, I just get S naught, right? So you have 1/2 g0 squared plus v naught 0 plus S naught. Oh, all you're left with is S naught. It's fine. So let's call that T1. Let's call this T2. So I can take the secant line between them, and that's my average rate of change of position over time. So that's my average velocity. Get it? Like position divided by time. Wouldn't it be velocity? Yeah, it would. Okay, so that's the secant gives me my kind of average velocity over that time interval. What if I have one in here, T3, that gets closer to my T1? So the closer I get, the more my secant line, or my average rate of change, looks like the tangent line. Oh, here comes my calculus. And the tangent line represents my instantaneous rate of change, or the instantaneous velocity. At that split second, what is the velocity? How fast is the person, the object going? Instantaneous. Okay. So to wrap it up, the secants are the average velocity, and that tangent is the instantaneous velocity. This makes sense. It makes sense. Think about slopes. You're taking distance over time. And we know how to get the slope of the tangent line. So actually, let me fix my mistake up there. We really are talking about, it's not the tangent to the curve is the instantaneous velocity, but the slope of that tangent line is the instantaneous velocity. Hope you picked up on that. And the slope of the secants are the average velocities, because again, it's this, the distance over the time, it's the slope. Okay, da and da, sorry, of course it's the slope. Da, 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 da. Because slope gives us a rate of change. We're talking about rates here. Velocity is a rate of change of position. Velocity is how fast your position is changing. Da, 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 da. Okay. So let's do an example. We'll use an example. Maeve jumps into a pool. Yippee! From 16 feet in the air. Yippee! At a velocity of 8 feet per second. So since it's positive, we're kind of assuming this is upwards, right? So 8 feet per second upwards. I jump up at 8 feet per second. My initial velocity, 16 feet high. So first, letter A, what's the position function? Letter B, what's my position after 0.6 seconds? Letter C, what is my velocity, my instantaneous velocity, as I hit the water? Alright, let's start with that position function. So S of t is going to be, well, we're in feet, so we're going to use 1/2 of that negative 32, right? G is negative 32, so 1/2 of negative 32 is negative 16. T squared plus V naught T, well, that's 8T plus S naught, which is 16. So that's my 1/2 G, using G equals negative 32 feet per second squared. The 8 is my V naught. plus 16 is my S naught. To get the position after 0.6 seconds, let me just substitute 0.6 in for t. So negative 16 times 0.6 squared plus 8 times 0.6 plus 16. That gives me, plug and chug, baby, plug and chug, 15.04 feet. So after 0.6 seconds, I'm at 15.04 feet from the ground. So I kind of go up initially, then I come back down, and that's where I am after 0.6 seconds. Well, so look at the velocities of the water. Don't I actually know the time that it takes me to get to the water? Yes, I do. Yes, I do, folks. Yes, I do. So let's solve for t when s is 0, because when I hit the water, right, so there's me. Hello! I'm a yippee! Look at my dress of a bathing suit as I jump off the cliff. There's my 16 feet high from the ground. There's the water in a little pool. So it's a pool. And I jump up initially with 8 feet per second, and I whoop, parabolic, come down. It's not a perfect parabola, but you get the point. Just a sketch. So by the time I reach the water, I'm at 0, position of 0. Okay, so I'm going to say 0, which is my final position there, is equal to negative 16t squared plus 8t plus 16. So I'm going to use the quadratic formula, or I could use a graph, but I want to figure out what t is when my position is 0. It's not easy to factor that, so we're not going to factor it. So using the quadratic formula by graphing, I get that t is either negative 0.78 or approximately 1.28. Yeah, okay, a negative amount does not make any sense for time. Throw that answer out. Does not make sense for time. Heck no. So we have my time. So if I have the time it takes me to get to the pool, now I can just figure out what my instantaneous speed is, or instantaneous velocity is at that moment. So remember, my position curve is that, so I want the tangent, I want the slope of the tangent, which is the derivative of the position curve. So I use my power rule, negative 16 times 2, I get negative 32t, plus, okay, 8t, that just leaves me with 8, plus 16, well that's just 0. Okay, so hope you understand that it's negative 32t plus 8. And this makes sense because it's g times time plus the initial velocity. Blah. It's using that kind of idea of rate times time. So not only is it a derivative, but it totally makes sense. So it's the derivative using those power rules we learned and the constant rule, but this totally makes sense. Think about the context, it makes sense. So to get my velocity, I'm going to take s prime over derivative at 1.28. That's a velocity at 1.28. That's negative 32 times 1.28 plus 8. And I get negative 32.96 meters per second. And I'm done. Thanks for listening. Be ready for tomorrow. The secret word, by the way, is pickle toes. I have no idea why. It just popped into my head. That's kind of disgusting. But yeah, pickle toes. Pickle toes, secret word. Have a good one.